right, thanks. Yeah, so my name is Shoumik. I'm an nth year graduate student now at Stanford. And I'm going to talk about using Rust for Weld, which is a high-performance parallel JIT compiler that we've been developing over the last few years. So just to provide an agenda for the talk, I'll first talk a little bit about what Weld is and what its motivations are, followed by the path that we kind of took that landed us at Rust. And then finally, I'll talk about some of the features of Rust that we use in Weld, and also where we hope to take the project from here. So jumping right in, the motivation for the Weld project is that modern data analytics applications combine many disjoint processing libraries and functions. So taking the the Python ecosystem as an example, a typical Python data science application may load some data in pandas and do some pre-processing, maybe train a machine learning model in scikit-learn, and then maybe do some statistical analysis in NumPy. So this is good because on one hand, you get great results kind of leveraging the work of thousands of authors who are implementing the best algorithms in each domain. But on the other hand, in these kinds of libraries, you generally don't get any optimization across individually written and optimized functions. So how bad is this problem that we don't get any cross-function optimization? It turns out that the growing gap between memory speeds on newer hardware and processing speed on new hardware is kind of making this rigid function call interface to these kinds of libraries worse and worse over time. So as an example of this, here's a pretty simple Python program. So it's using pandas to parse a CSV and then drop some null values, and then it's using NumPy to compute a mean. And realize for these like Python and kind of data science style libraries, there's nothing like trait iterator, right? The interface to these libraries is you have some functions and you throw some data at them and they crunch some numbers and give you back a result. And because of this, when you actually look at the execution of these like typical data science type workflows, it looks something like this. You have some memory sitting around and you call a function, and basically what that entails is that you give it some data, it processes something, and then it gives you back a result. When you call another function, you basically do another entire scan over your data set, go back to main memory, load those values back into the CPU cache, into the registers, compute some more values, and then again, store the values back. And if you have these large data sets, what ends up happening because of this gap between memory access speeds and processing speeds is that you actually spend most of your time just accessing memory instead of actually doing meaningful work on the CPU. And for these kinds of workloads, we found up to 30x slowdowns in popular libraries such as NumPy, Pandas, TensorFlow, all these kind of data analytics libraries that you hear about, compared to an optimized just C or Rust implementation. So if I were to take the same application and write it in C, there would be this huge kind of gap between what people actually use to this kind of stuff today and what the hardware is actually capable of. So Weld is a common runtime for data analytics libraries that kind of attempts to tackle this problem. And the approach that Weld takes is something like this. There's these libraries for different domains, just SQL or machine learning, and they effectively target a common parallel runtime. And instead of executing each function individually, this runtime will act like a standard compiler. It'll look at all your code just at runtime instead of at compile time, and it'll basically run an optimizer over it and JIT code to execute during the execution of your application. And you can JIT code for these different kind of parallel platforms, such as CPUs or GPUs or something else. So internally, Weld has a bunch of components. The first one is this runtime API that developers of libraries use to actually submit work into Weld. The second component is this Weld IR. So this is basically like a parallel kind of functional small programming language that developers of libraries use to submit work into the runtime. And I'll talk a bit more about that in a bit. And the final component is this optimizer, which is basically like a standard compiler optimizer, which takes the IR and kind of just transforms it into a basically more efficient version of the same IR, and then that's sent over to the backends, and the backends use something like LLVM to do code generation. So if we look at kind of the 1,000-foot view of how a program using Weld executes, it starts with some user application that's unmodified. So the idea here is that for users, Weld is kind of invisible, but for library developers, you're replacing the implementation of your library functions to integrate with Weld. So let's say we have a function with some Weld-enabled libraries. When a user calls a function, instead of evaluating those functions, internally those function calls will kind of submit these fragments of IR code into the Weld runtime. When you actually want to evaluate this, so this might be when you say want to print something to the screen or send it over the network or whatever, the runtime will basically figure out that there's these data dependencies between these lazy computations, and it'll combine them into a single program, and then it'll fire up the optimizer, optimize that program, and then JIT some code. And that's what the data in your application actually interacts with. And then there's also this kind of managed parallel runtime that hooks into this thing, because we're actually generating code that's meant to be run in parallel. So there needs to be a runtime to do things like scheduling and task management and memory management and all that good stuff. So when we started with Weld, it was kind of meant to target these cross-library optimization-based workloads. But over time, we've kind of seen that it's been useful for other things as well. So as a few examples, we've seen people use Weld to build JITs or new physical execution engines for databases or analytics frameworks. We've seen it being used just within individual libraries. So if you just want better kind of native code execution in a Python library, using a JIT compiler is a great way to do that. So we've seen it being used for that. And we've also seen it being used to target new kinds of parallel hardware. And the reason that Weld is especially nice for that is because the IR is just structured in a way that it can assume that a bunch of things are inherently parallel. So if you have hardware such as GPUs or vector accelerators, the IR is kind of an attractive way to kind of bridge high-level code with the kind of machine-specific code. So just quickly to provide some context on the kinds of speedups Weld could provide. These are obviously cherry-picked benchmarks to make us look better, so take them with a grain of salt. But in this like Kaggle type competition, where we basically do some data cleaning and linear algebra and NumPy and pandas, we saw 180x speedup here. So this is because we parallelized the single-threaded libraries NumPy and pandas, but it's also because we can do optimization such as loop fusion that like iterators in Rust can do, for example, but it's doing them over these kind of native Python libraries. And I also want to point out that pandas and NumPy are written in C internally, so this isn't like comparing against like some weird Python loop or something. As another example, we were able to optimize this image lightning plus linear regression workflow in TensorFlow and NumPy. And this is comparing against TensorFlow's own kind of XLA compiler. So TensorFlow already has this compiler that it uses to do things like operator fusion. But because we can actually look across library boundaries, we still get a pretty nice speed up here. And finally, we can also use Weld to kind of just optimize the execution of things like data analytics frameworks. So here we integrated it with Spark SQL, and we can basically get some native code execution in Spark. So instead of relying on the JVM, we're executing like vectorized native code. So we get some nice speedups there. OK, so just to provide some more context for the rest of the talk and to show how the optimizer kind of functions, I'm going to do a quick demo where we compile a Weld program using this REPL that we've built. So I'll switch over to that now. All right, hopefully that's readable. So OK, I have to look at this. All right, so here's the REPL. So basically, you can just type in Weld programs here. So here's a simple one that just adds one to input. And you can see that it basically just dumps out some information on things that it's doing. So here it did some macro substitution, followed by type inference. So this isn't going to look super interesting because this program is pretty simple. But you can hit enter and kind of walk through the different passes that the compiler applies. Here it's not really going to do much because it's kind of hard to optimize adding one to a number. But you can also get some stats about how the compiler does there. So if you look at the right side here now, there's a slightly more complicated program where we're computing the sum of squares. So that first line with the map is basically squaring each integer that we pass in, and the second line is summing the squared integers. And you might be wondering why we've actually written this program in this way, right? Why didn't we just write a single loop that does this right off the bat with A? So remember that Weld is meant to be integrated into these kind of higher level libraries. So this is kind of how you can expect a typical Weld program to look. So for example, a NumPy program a NumPy function that squares things might generate the first line of this program, and a NumPy function that computes a sum might generate the second line. And it's up to Weld to kind of look at these individual fragments and come up with something more reasonable. So we'll go ahead and load this into the REPL. So I'll just hit load demo.weld here. And right off the bat, you can see that this program looks fairly different from what we have on the right side. So here we've done macro substitution and type inference. And the reason this program looks so different is because map and sum in Weld are actually macros that expand into these parallel for loop operators. So you can see there's that for operator there. And that just means that we're iterating over the input that we give it in parallel. So that first for loop is iterating over A in parallel, and it's using this thing called an appender to basically append items to a list. So that's our kind of map that constructs the squares. And the second for loop is actually doing the sum. So that merger with the plus in it, that's just a way to represent a parallel aggregation in Weld. So these are just details about the IR that I'm not going to spend too much time on. But that's basically how a program looks like in its kind of unvarnished form. So we'll now step through the optimizer and look at what it does. So this inline let pass as an example got rid of the assignments, and it kind of inlined those loops. But we still have those 2 passes over the data. Stepping through it a couple more times, you can see this loop fusion pass, which is probably the most interesting one in this example, actually got rid of one of the loops, and it inlined the squaring of the input into that aggregation. So now we're just doing 1 pass over the data. So we'll step through it a little bit more, and you can see that it also vectorized this thing by basically introducing these SIMDiator things that allow the backend to generate SIMD code. And finally, we get some statistics about how the compiler did. OK, so that's kind of a 1,000-foot view of what Weld is and how it works. All right, so switching a little bit to the implementation side of things, the first kind of Weld compiler implementation was in Scala. So I'll briefly talk about what was good about Scala, and then I'll talk about what was bad and why we ended up with Rust. So the good things about Scala, the main reason that we chose Scala to begin with was because it had these algebraic types and this really nice pattern matching mechanism. So all those rules that I showed you in the demo, those are basically just pattern matching rules where you look at some subtree of a program and you substitute it with another tree. And that other tree just happens to be more efficient, but it computes the kind of same result that the first tree computes as well. Other kind of auxiliary reasons, it already had like a large ecosystem. So with Scala, you can use all the things that Java has, and it also had things like collections and everything, so that just makes building stuff easier. And also, my advisor liked it, so that obviously impacted things as well. So going back to this pattern matching example, here's an example of converting a Boolean expression into a short-circuited version of that Boolean expression. So as an example, this AND expression, it computes left and then computes right, and then it takes the AND and then returns either true and false. So if we want to convert this to a short-circuited expression, we can convert it to an if statement where it evaluates left. If left is true, we evaluate right. And if left is false, you just return false. Okay? And you can see that writing these kinds of pattern matching rules for an optimizer or these kind of correctness rules as well is super natural both to read and to write. And this was kind of the main reason that we chose Scala to begin with. And when I talk about the Rust part, you'll see that it also influenced the design of how we designed to structure the compiler in Rust as well. OK, but this is a talk about Rust. And so naturally, there are some bad things that we ran into that led us to move on. And kind of the main bad thing about Scala was that it was very hard to embed into other things. And hindsight is 20/20, but we should have known this. But it's not great if you have some Python program running and you want to compile something and you have to fire up like a 100 megabyte JVM process to do that. So that was probably the biggest reason why we decided to move away from this kind of managed runtime world. Auxiliary reasons, JIT compilation times we also found were pretty slow for larger programs. For smaller programs, it didn't really matter. And this was, again, just due to the fact that we were actually interpreting code. And usually, we weren't running things enough for the JVM to compile things to native code. We had a managed runtime. This feeds back into the first reason. But it also makes things like writing FFIs very difficult. It had a pretty clunky build system. I don't know if anyone's ever tried to use SBT here, but I'm not going to say more about it. Finally, the runtime also had to be in a different language, right? So we're JITting code, and this JIT'd code is just some arbitrary machine code that's expected to be scheduled by some kind of threading library. And there's no way that we were going to use like Java threads for that, because that's just not fun. So effectively, we wanted to redesign the JIT compiler, the core API, and runtime from the ground up because of these kind of shortcomings of the language that we were using. But if you think about it, these 3 things have some fairly different requirements. The JIT compiler needs things like pattern matching and algebraic data types, so it's nice to express these kind of optimization rules. The core API, because we want to integrate it into other things, needs a nice C-compatible FFI. And we also need strong support for parallelism and also the ability to control kind of low-level things like memory layout. Okay, so I think everyone knows where I'm going with this. So this was kind of what led us to Rust. Just kind of really quickly reiterating the requirements we had. These are in no specific order. We needed speed because compilation happens at runtime. So this isn't some offline compiler, right? The compilation time actually counts toward what the user sees. We needed safety because we were embedding things into other libraries. We did not want to manage runtime, again, because we were embedding this into other runtimes. We wanted a rich standard library, functional paradigms for things like pattern matching, and also a good managed build system because of the kind of struggles that we had with SBT. So we started our search for a new language. And these are kind of the languages that we considered off the bat. But going through our requirements, it was pretty easy to kind of knock these off. Right? So we wanted things to be fast, so that got rid of Python. We wanted it to be safe, so we said goodbye to C++. We didn't want to manage runtime, so there went Golang and Java. And we were basically left with Swift and Rust. And recall that this is back in like 2016 or something, so it was a slightly different landscape back then. We wanted a rich standard library. We wanted these functional paradigms for things like pattern matching, so both of them kind of had that back then. And we also wanted a good package manager, and this isn't on the slides, but after we started using both of these and evaluating them, we realized that we also wanted a good community. And that's kind of where Rust really won out. The ability to have crates.io and these super high quality packages, and also the Rust forums and everything to have people help us with stuff, and also the ability to ask questions that weren't related to iOS development. All that stuff was pretty nice, and it's kind of what sold Rust for us at the end. OK, so I'll dive a little bit into how we actually use Rust for building Weld now. So the first iteration of Weld and Rust was basically just looking at the compiler. So we took all the Scala bits of our code, and we ported them over to Rust. So this involves the core API, the optimizer, and also the compiler backends. So to begin with, just because we were trying things out, we decided to keep the C++ runtime to do things like thread management and memory. And we basically just had some thin bindings between the main kind of compilation part and the actual runtime part. To build bindings that we had from before, so we had bindings for Java and Python. We basically built a C API, and I'll talk a bit more about how we did this in a few slides. And then these C API bindings basically just mapped into our existing bindings for languages like Python and Java. OK, so going into a little bit more detail now, the Weld IR itself is implemented basically as a tree with all the operators represented using an enum. So the main kind of construct in the IR is this thing called an expression, or expr, that has a kind, that's the kind of expression it is, and a type, such as integer or float or whatever. And expr kind itself is basically this giant enum that defines all the different kinds of operators that we support. So you might wonder why we actually did it this way. Another kind of straw man way of doing it is to use something like trait objects, which is arguably more extensible. So if we want to add more things, we don't have to go and update this enum everywhere. And this kind of goes back to the pattern matching thing I was talking about a while back. These enums make pattern matching super easy. And basically, because so much of the compiler has to do with the optimizer rules, this was kind of a first-class concern for us. So diving into that a little bit more, we were pleasantly surprised that the pattern matching rules were fairly similar to Scala, despite having to get around the borrow checker and everything. So in most cases, this is the same rule that we had from before. It's basically converting binary operations into short-circuited operations. All you have to do is match on a target pattern, create a substitution, and then replace the expression in place. So there was one kind of quirky thing that we had to deal with in the beginning while we were learning Rust, and that was learning to live without clones. And we found that this was especially difficult with these kind of tree and graph data structures, just because it's an easy escape hatch. So our old code for this transform looks something like this. And if you squint at this code, you can see that what it's basically doing is that it's taking your entire subprogram and copying it every time this pattern matches, which isn't great. But there's kind of two things wrong with this. The first is that it's kind of tricky to avoid, at least for us when we were newcomers, because these data structures are kind of pointer-based and you have to deal with the borrow checker. So we knew in the back of our minds that there was some combination of ref and refmut and nmut and whatever to fix this. But it was easier just to drop in some clones in some well-chosen spaces and get the borrow checker to shut up for a couple weeks. But unfortunately, the other bad thing is that this is especially fatal for performance, because we're fundamentally dealing with recursive data structures here. So this ends up becoming a recursive clone. So at some point, we did have to fix these issues. So our solution to this was fairly simple. We have this take call now. And basically, all it does is you create a placeholder expression, and then you use this mem swap to swap it out, and you return the old thing. So you can basically drop in take in most places where you use clone, and as long as you're replacing that old expression that you're substituting, this is basically like a pointer swap. And this obviously gives us some pretty substantial performance benefits. It was just, as newcomers to the language, it was hard for us to kind of find these kinds of things. I think Steve in his keynote even said that mem swap used to be part of the syntax a few years ago, and I can totally see why that's the case, right? It took us like probably a year to find that this mem swap utility even existed, and it's our fault for not asking. But now that we have it, performance is great, and our rules are also easy to write, so we're pretty happy. Other things, we use LLVM C API for code generation, and it's pleasantly easy to interface with C libraries. And again, this is in large part thanks to Cargo. So Cargo has these -sys crates. It's just a paradigm in Cargo, where a -sys crate is basically just Rust definitions of a C library. So here's some code that you don't have to read, but it's basically taking a struct and generating code for creating that struct. And embedded in there are two kind of LLVM C API calls. And it was very natural just to call C from Rust, and also the other way around, which I'll talk about. And that kind of made it easy to kind of take the huge ecosystem of C libraries that are out there and use them in cases where the same thing in Rust didn't exist. FFIs are also very easy to build compared to Scala, where we needed things like these weird wrapper objects. We needed to tell the GC not to throw our stuff away, and so forth. In Rust, we basically define some type. You can easily specify how long you want that type to be. We made an alias for it. And then you basically create a function that allocates some memory on the heap and then forgets about it. So for a Rust developer, this is evil. But for people who use C, this is very natural, right? You call a function, it allocates some memory on the heap, and you're responsible to write it down in your notebook and free it somewhere else. So it's a very thin layer of kind of connecting the C world, where giving an interface to C developers that they're comfortable with, and also kind of the Rust world, where everything above this is just pure Rust, and you don't have to worry about this stuff anymore. And I also want to say that you can almost certainly automate this kind of stuff with procedural macros, though we haven't tried. So if anyone knows of any crates that does stuff like this, please let me know. Okay, finally, we use Cargo to manage literally everything about our project. So the FFI that was generated on the previous slide, that's a header for that is generated using a build.rs file. We use workspaces to build tools automatically. So literally all you have to do to get the tooling and the compiler and the runtime is you git clone and cargo build release, and everything is just there sitting, waiting to be run. So that's really nice. Docs and testing, all that standard stuff, we also use Cargo for. Yeah, I love Cargo. I think it's probably one of the most underrated features of Rust, just because it's so easy to use and get started with. So, people often say that Rust is one of the harder programming languages to learn today. I've been writing C for 10, 15 years now, and I still don't know how to write a proper makefile. So, yeah, if you think that learning Rust is difficult, yeah, try to write a makefile or autoconf or CMake or whatever those other things are. It's not that easy. So overall, life was pretty good, but we still had that pesky C++ runtime, and that led to the usual host of issues. So we had concurrency bugs that were unrelated to the generated code. We had two code bases, which wasn't fun. We had a more complex build system, so we still had some nested makes left in there somewhere. We had two logging and debugging systems, so just like small usability things like that. So our second cut of Weld in Rust actually ported the entire runtime to use Rust as well. So the fundamental kind of architecture picture looks the same. It's just that we've replaced the chunk that was in C++ and we've kind of moved it into Rust. And this gave us some advantages. It's safer than C. There's really no guarantees when you're interacting with this arbitrary JIT'd code. But it's definitely, things like scheduling and task management are definitely safer than they were before. We also have a nice single logging and debugging API. So you can set a log level in the Rust compiler, and then you'll get the kind of same logging output for when you're running generated code, which is nice. And it's also easier to pass data from the runtime to the compiler also. So this was easy enough before, but this lets us do things like asserting that the size of some generated struct in our compiler matches the size that we expect in like a unit test or something. It's like kind of clinky stuff like that that just ensures that stuff is clicking. So a little bit of detail on this. So the way that this runtime works is as follows. So you basically JIT some machine code, and then you basically call into Rust using these FFI style functions. So on the Rust side, you basically have this type definition, and that's all. There's this JIT func type definition. And this basically refers to a function pointer that is generated somewhere by the actual JIT compiler. So there's some function somewhere that was generated because you took some Weld IR and you compiled it into the memory of the existing process. And then you have this run task function, which is a standard everyday Rust function, except it has this C wrapper as well. And by wrapping it as like a FFI function, you can basically call that function from the generated code. So this is what that looks like. This is kind of scary looking, but it's not that bad. You basically have this function F1 that's generated via the JIT, and then you have some code that does some unpacking and stuff. And then you have the run task function. So run task basically takes F1, which is a function that we generated, as a input. So this is just a pointer. And run task is just written in Rust. So now we can do our standard Rust stuff here. So we can use the standard Rust library to spawn threads. We can time tasks, do load balancing, use stuff from crates.io, whatever. The only funky thing is that we have this call to F1 at some point, which from Rust's perspective is just this kind of black box function that it's calling. And it really just ends up calling into some code that we generated. So this obviously needs to be wrapped in unsafe. But it's pretty nice just because you get to kind of unify the compilation part and the runtime part of this stuff. OK, so if you're interested in this stuff, we'd love contributors. We have around 30 contributors today, over 1,000 GitHub stars. So the project is definitely still growing. There's many, many things to do, ranging from compiler optimizations to fleshing out things like GPU support. And we also have contributions by many other groups in academia and industry. So I think we can find something to do no matter where you are. I also just want to give a quick shout out to the other people at Stanford who contribute to this project. Obviously, none of this would exist without them. And yeah, just to conclude, Rust we thought was a fantastic fit for building kind of a modern high-performance JIT compiler and runtime. Has these nice functional semantics for building a compiler. It also has the native execution speed, which is important for the runtime, but also for the JIT compilation part. And it also gives you the kind of low-level control you need to build these kinds of things. And finally, it interoperates fairly seamlessly with C, which is important for hooking into other languages. So the link to the code and the website and stuff is up there. My email is also there. So if you have any questions, feel free to reach out. Thanks.